So that concludes our section on mechanics and materials, and now let's move on to failure and fracture. So this is actually going to be part 1 of failure and fracture. You'll see part 2 2 weeks from now. So let's move on to problem 4. Problem 4 says the tensile strength of brittle materials may be determined using a variation of the equation below. The equation below reads as follows. The fracture strength of a brittle material is equal to 2 times the applied stress multiplied by A, which is the critical surface crack length, divided by rho t, which is the critical crack tip radius, all to the power of 1/2. So the problem says compute the critical crack tip radius for an aluminum oxide specimen that experiences tensile fracture at an applied stress of 275 megapascals. Assume that the critical surface crack length is 2 times 10 to the minus 3 millimeters, and the theoretical fracture strength is equal to E over 10, where E is the modulus of elasticity. So this is a very simple problem. You're given the equation, you're given all the values, all you need to do is substitute the givens and solve for your unknown. So let's rewrite the equation. So sigma m is our fracture strength, is equal to 2 times our applied stress times our critical surface crack length divided by our critical crack tip radius, which we're solving for, all to the power of 1/2. So the problem tells us that the theoretical fracture strength is equal to E over 10. So we can say that E over 10 is equal to 2 times the applied stress times A over rho t to the power of 1/2. Just a simple substitution. So now we need to rearrange for rho t and substitute our unknowns. So we can say that rho t is equal to 400 times our critical surface crack length times our applied stress squared all over our Young's modulus squared. So now we have our critical surface crack length and we have our applied stress, but we don't have our Young's modulus. So we're given this table on the side. So here's what we're going to do. We're told that it's an aluminum oxide specimen. So here's our aluminum oxide. And we're dealing with ceramic materials. So we know that our Young's modulus in gigapascals is going to be 393 gigapascals. So now we have all of our unknowns. We can simply substitute the values and solve for our critical crack tip radius. So rho t is equal to 400 times 2 times 10 to the minus 3 millimeters times our applied stress, which is 275 megapascals, all over our Young's modulus, which is 393 gigapascals. Now, make sure you change this to meters and this to pascals and this to pascals before you click enter on your calculator, or else you're going to get a value that's meaningless. So simply plug and chug. You're going to get a critical crack tip radius of 0.39 nanometers. And that is the final answer to problem 4. Now let's move on to our 5th problem. So our 5th problem says, some aircraft component is fabricated from an aluminum alloy that has a plane strain fracture toughness of 35 megapascals per root meter. It has been determined that the fracture results at a stress of 250 megapascals when a maximum or critical internal crack length is 2 millimeters. For the same component or alloy, will fracture occur at a stress level of 325 megapascals when the maximum internal crack length is 1 millimeter? Why or why not? So this is a very typical exam problem. All you have to do is compare this fracture toughness that you know that would be somewhat from a data sheet to a test that you're performing on the same component with different test conditions. So we need to establish an inequality. So if the test you're performing has a fracture toughness greater than the plane strain fracture toughness, then you know fracture will occur. So let's write that. So our fracture toughness of our test, if it's greater than our plane strain fracture toughness, then failure will occur. So now we need to prove this equality true or false with the conditions that were given. So we know our plane strain fracture toughness is 35 megapascals per root meter. So we're good. We only have one side of the equation to calculate, which is our fracture toughness of our test conditions. So fracture toughness of our test is equal to our geometry factor times our applied stress multiplied by pi times our crack length. So in the question, we're given the applied stress and we're given the crack length. However, there was no mention of the geometry factor. But the plane strain fracture toughness that was given to us and the test is on the exact same component. Therefore, the geometry factors will be the same. So we can use some of the information that was given to us about the plane strain condition, solve for the geometry factor, and then use that to find our fracture toughness of our test condition. So let's say that our plane strain fracture toughness is equal to our geometry factor times our stress times pi times our crack length. Let's solve for our geometry factor. So we can say that our geometry factor is equal to our plane strain fracture toughness divided by our stress times pi root pi times our crack length. So now all we have to do is substitute our values. So 35 megapascals per root meter divided by our critical stress, which is 250 megapascals, times root pi A. Now, A is crack length, but we're given internal crack length. So therefore, we need to divide this internal crack length by 2. So we're going to do 2 times 10 to the minus 3 divided by 2, and that's going to give us an approximate value for our geometry factor of 2.50. So now we can substitute this value into our test conditions and solve for our fracture toughness of our test. So K test is equal to 2.50 times the stress of our test condition, which is 325 megapascals, times, times root pi, and again, we're given internal crack length, so we should do 1 times 10 to the minus 3 meters divided by 2. And that's going to give us a K test of 32.2 megapascals per root meter. So, with the results that we get, we can see that our test conditions produces a fracture toughness which is less than our plane strain fracture toughness, and therefore failure will not occur. So there's one more thing that I want to mention. It is very important that we always use the correct units. So when I'm solving these problems, I go very quickly and I may not change the units all the time. So let's just go back and look them over one more time. This is in megapascals, this is in megapascals, and I change this to meters. So we're okay. If we come over here, I'm in megapascals and we're in meters and we're okay. You can also, if you want to, work in pascals, which is what I recommend. So change this to pascals, change this to pascals, change this to pascals, and you're always going to be in the correct units. And that is the end of problem 5. All right, let's move on to our final problem of tutorial number 1. So problem 6 reads, a Sharpie impact test was conducted on a tempered 4340 steel alloy. The data that was collected from the experiment is tabulated. Once the data was collected, an impact versus energy graph was plotted to better observe the results and is shown below. So this is a typical impact energy versus temperature curve. So part A says, determine the ductile to brittle transition temperature as the temperature corresponding to the average maximum minimum impact energies. So we need to get an average. The way we get an average is the maximum value on the graph plus the minimum value on the graph divided by 2, and that's going to be our average. So we can say that our average impact energy is equal to maximum value plus our minimum value divided by 2. So if we look at the graph, we can see that our maximum data point is right here at 105 joules. And our minimum data point is down here at 24 joules. So plus 24 joules divided by 2, that's going to equal 64.5 joules. So that's our impact energy average. So we're going to use this value and come on our graph and determine our ductile to brittle transition temperature. So 64.5 is approximately here. So we're going to come across, and then we're going to come down, and we can see that our ductile to brittle transition temperature at our average is equal to negative 100 degrees C. So that's what we conclude from part A. Now part B says, determine the ductile to brittle transition temperature as the temperature at which impact energy of 50 joules. So we're going to come to where we see 50 joules, which is approximately here. We are going to come down, and this value we can interpolate to be negative 114. So our ductile to brittle transition temperature that corresponds at an impact energy of 50 joules is equal to negative 114 degrees C. And that's the end of this problem. As you can see, it's very straightforward to read these curves and read these graphs. I just want to point out that this purple curve fit is very poor, and that's why I tried to choose the values of our maximum and minimum that correspond to the actual data points that we have, because we do have a lot of overshoot here in our curve fit. So on a test or an exam, you would probably have a better curve fit or no curve fit at all, and then you could just go in and actually sketch the curve with a pencil or pen, and you'll probably get a more accurate result. So like I said, that concludes our tutorial number 1, and I hope you guys enjoyed. I hope you guys have learned a lot, and I'll see you again in 2 weeks.